Now, you recall that when last we talked, I brought up Galileo's first theory of the cause of gravity, the why of gravity, and that was that all around the Earth, a wind was being drawn into the center of the Earth. For some reason, the Earth was literally sucking on some sort of air in space, and it was all going inside of the Earth. And as the wind blew down towards the surface of the Earth, it exerted a force on everything near the surface and dragged it along with it, just like the wind will drag leaves. And I asked you if that was an acceptable theory of gravity. And at first it seems that it is, if you think about it. Each little atom inside of an object, remember Galileo had this idea of mathematical points that in a crude way corresponds to our idea of atoms, that each atom in an object would feel this wind blowing around it and be drawn down into the Earth. But then Galileo, he actually published this theory. He published it fairly wide. I think he published it in Italian, so a lot of people could read it, instead of Latin, so only a few people could read it. But after he began to think about it, he began to have doubts that it was true. Now, what made him doubt that this wind theory of gravity was true? Well, let me tell you something about the wind. If I have a balloon in my hand and the wind is blowing this way at 10 miles an hour and I let the balloon go, then the balloon will go faster and faster and faster this way and this way. But will it keep on going faster forever? No, it won't keep on. After a while, it'll get up to 10 miles an hour, which is the speed of the wind. And what will happen then? Then it won't go any faster. It'll just get 10 miles an hour and go. Whatever the speed of the wind is, that's the fastest things can fall. When a ship is sailing at the speed of the wind, at least if it's sailing in front of the wind, then it can't go any faster, sailing directly downwind. But is that really true? If you drop objects, do they just get up to a certain speed and go no faster? Well, of course, if you have a parachute, it gets up to a certain speed and it doesn't go any faster because of it drags on the atmosphere. But if you have a heavy rock, as far as we can tell, it will keep on going faster and faster and faster and faster. It doesn't seem to go up to a certain speed and quit. It seems to keep on getting speed the further it goes. So that seems to be a difference that you can't explain gravity by a wind. But there's still a greater objection, and I'll show you what that is. Supposing the wind again is blowing 10 miles an hour this way, and I just let the balloon go, then the balloon will begin to go faster and faster until it gets up to the speed of 10 miles an hour that way. But suppose I have the balloon and I take it and I throw it that way, and I throw it that way at, say, 20 miles an hour. So I throw it that way at 20 miles an hour. Now what does the balloon do? What does the balloon do? It's going this way 20 miles an hour to begin with because I threw it that way. Now the balloon is moving faster than the wind. So as seen from the balloon, the wind is blowing backwards because the wind's only going 20 miles an hour. The wind's only going 10 miles an hour. The balloon's going 20 miles an hour. So seen from the balloon, the wind is blowing the wrong way. And it exerts friction on the balloon. And what happens to the balloon? The balloon, in that case, slows down. And how far does it slow down? It slows down until it's only going 10 miles an hour that way. So if I take a balloon and I throw it 20 miles an hour with a wind going 10, then the balloon doesn't accelerate. In fact, the balloon leaves my hand at going 20 miles an hour, but it slows down until it gets to going 10, and then it keeps that speed. Now, if that were true of gravity, then there would be some speed. I don't know what it is, but there would be some speed, and if I took this eraser and I threw it down faster than that speed, the effect of gravity would not be to make it go still faster. The effect of gravity, if it were caused by a wind blowing downward, would be to take the eraser, if I threw it faster than the speed of that wind, and make it go slower until finally it got to the speed of the wind, and then it would continue on down at that speed. And Galileo thought to himself, gee, that's crazy. That means that there is some speed, and if I throw an object down faster than that speed, the effect of gravity will be to make it go slower instead of faster. I can't believe that. That doesn't make sense. And so Galileo concluded that probably gravity was not caused by a wind. Probably gravity was not caused by a wind. He tried to figure out what could be the cause. What What could be the cause of gravity? And he never was able to do it, though it's a little bit like the story of Einstein working on the unified field theory. He never was able to figure it out. And so Galileo, thinking about the cause of gravity, was never able to figure out the cause of gravity. Though no doubt he thought about it for the rest of his life. He could never figure out the why of gravity. He just didn't quit. A first-rate scientist wants to figure out why. But if you can't figure out why, then scientists do something that is second best. And what's that? I will tell you what they do that's second best. Instead of explaining why, they just give the rule. In other words, they figure out an equation to describe the thing, and they say, we don't know why this equation works, but at least we know the exact rule. So that's what Galileo tried to do. Instead of figuring out the cause of gravity, he tried to do what's second best and just give the rule describing gravity. And I want you to pay attention. He said, what would happen if you drop an object is it keep on going faster and faster forever. Of course, forever means until it hit the ground, or if it went into a well till it hit the bottom of the well, that's forever for the rock. But as long as it could fall down, it would keep on going faster and faster. And he got that idea because, of course, that was the one thing that the wind wouldn't do. And then he said, now I'm going to give the rule for that. And I want you to pay attention to the rule. Here comes the rule. If an object falls for a certain distance, like 1 foot, it falls down 1 foot from the top, it has a certain speed when it falls down 1 foot. And then when it falls down 2 feet, now it's gone down 2 feet, it's going faster. In fact, it's going twice as fast. And now if an object falls down 3 feet, it's going 3 times as fast. And if it was 4 feet, it would be 4 times as fast, and 5 feet, 5 times as fast. In other words, the speed of the object increases in proportion to how far, how much distance, how many feet the object is falling. And Galileo said that is the law of gravity. That's the law of gravity. And he again published it, and he said, now, that's it. And he got to thinking, and he thought more and more, and then he became unsure if even that was the law of gravity. Never mind the reason. There was no reason, but was that even the right rule? And he got suspicious that maybe that wasn't the right rule for gravity. Now I ask you, what do you think? Do you think that's the right rule for gravity, or do you think that's the wrong rule? Well, Galileo thought. And after a while, Galileo decided that that was the wrong rule. Why did he decide that was the wrong rule? You'll say, oh, he did an experiment. No, he didn't do an experiment. Experiments are much overrated. If you've ever done an experiment, you know how well they work. But that aside, why couldn't Galileo do an experiment, drop an object and see how fast it would go? Because if you think about dropping an object, it turns out when you drop an object, it will fall about 16 feet in 1 second. Now, most rooms and places where you experiment are probably about 16 feet high at best. You have 1 second. Could Galileo time 1 second? Any high school, the most poorly equipped high school in the United States, the coach has a stopwatch that measures seconds. Or in the dark room someplace, they have a clock, or somebody has an electronic watch that they bought at a drugstore. Somebody gave them that will measure seconds in the worst high school in the whole United States. But did Galileo have a device that could measure seconds? And the answer is no, because in the days when Galileo lived, pendulum clocks had barely been made to work, and there was no simple device for measuring seconds. You think you're going to measure your pulse, you're going to use first of all, you can't find your pulse. That's the first thing. But even if you do find your pulse, it's no good for measuring seconds. You cannot do accurate experiments with your pulse. And in the days of Galileo, talking about an accurate timer was like us talking about something in the future. Maybe we'll visit a star someday, but there's certainly no rocket ship now that will go to a star. And it was the same thing. Maybe someday people will make clocks that will measure seconds, but in the days of Galileo, nobody could measure seconds. If you can't measure seconds, you can't really do a falling body experiment. So he couldn't do it. So what made Galileo realize that this law was wrong? Remember, the law is you fall 1 foot, you have a certain speed. You fall 2 feet, you have twice as much speed. You fall 3 feet, you have 3 times as much speed. Well, he wasn't sure it was wrong. He just had a suspicion that it might be wrong. And this is why he got the idea that this law could not be. Not from an experiment, but just from thinking about it. See, Galileo was a theoretical physicist. And he liked to think. You see, these scientists, they have sort of a prejudice. You always say that they like experiments, which is not true, because experiments are a big hassle to do. It's much easier to think. And this is what he thought. He said, look, this is Galileo's thinking. He said, if I drop an object and it falls 1 foot, it will have a certain speed. I don't know what, but some speed. But if it falls only half a foot, that is down to here, then it would only have half as much speed. But if it falls just a tenth as much, then it would have just a tenth as much speed. But before the object starts at all, when it's still up here, what speed does it have to begin with before it's fallen at all? The answer is 0. That's the speed it has to begin with. Now, if you're going 0 speed, how long does it take you to go a foot? At 0 speed, how long does it take you to go a foot? You never get there. It takes you forever. Isn't that right? At 0 speed. Now, at 0 speed, how long does it take to go half a foot? Same thing. It takes forever to go half a foot at 0 speed. How long does it take to go a tenth of a foot at 0 speed? That takes forever too. In fact, at 0 speed, if I give you any distance at all, the time that it takes to get there is forever. But the only way you're going to get the tiniest little bit of speed to begin with is by going down a little bit, because remember, the speed comes from going down. But if you start with 0 speed, you can't begin going down, so you can't begin to get speed. And an object, if this were truly the law of gravity, then if you had an object here and let it go, it would not begin to fall. Now, that's not surprising. There's a lot of things in the world like that. Of course, if you hit the object, then what would happen? If you hit it, you'd start it down and begin going faster and faster and faster. And as I say, in the world, there are things like that. A gasoline engine will not start by itself, but if you get the engine started by giving it a little turn, then it'll begin to go faster and faster and faster. Same is true for old-fashioned electric motors. They were not self-starting either. You'd have to twist them. Now they start by themselves. But in the olden days, you actually had to start them spinning, and then they would rev up from there. So it could have been that God could have made a world in which objects do not fall by themselves. You have to hit them, and then they begin. God could have made a world like that, but he did not. In our world, the real fact is that objects start themselves. That's the actual fact. And if that is true, then this rule of gravity has to be wrong. This could not be the right explanation of even the rule. Never mind the cause. This is not even the right rule for gravity. So finally, Galileo thought and thought, and now he had been wrong. Remember, his thinking on gravity, such a simple thing as just what makes objects fall. Here, the smartest man who ever lived, or the second smartest man who ever lived, Galileo, had been wrong about it not once but twice. First, his wind theory was wrong, then his mathematical expression that the speed's proportional to the distance was wrong. So now he thought again, and he had a third idea. He said that as an object falls, it goes faster and faster, but after it's been falling for 1 second, not 1 foot, after it's been falling for 1 second, it has a certain amount of speed, after it falls for 2 seconds, then it has twice as much speed, and after it falls 3 seconds, it has 3 times as much speed, and 4 seconds, 4 times as much speed, 10 seconds, 10 times as much speed. 10 times as much as what? 10 times as much as the speed it had the first second. And that's the idea of gravity. What's the advantage? What good does that do? That does this good. When an object first begins to fall, it's not moving through space at all, and therefore you can't say that the speed comes from moving through space, because it's not moving through space when you let it go. But the object is moving through time. Even as if it stands still and I let it go, it's moving through time. And if the speed comes from moving through time, since it's always moving through time, then it moves through time and it picks up speed from moving through time. And if it moves through time twice as much, 2 seconds, it's picked up twice as much speed. And if it's moved through time 10 seconds, then it's picked up 10 times as much speed. So that was why Galileo went over to time. I want to tell you 2 things. I want to tell you, first of all, that this was the first time that time came in to physics. Heretofore, it was felt that time was basically something in people's heads. Not like your mood, but a little bit related to your mood. And if you know one thing about physicists, they say if you do an experiment, a real experiment, it doesn't depend upon your mood. Now, some people will say if you cook a dinner and you're in a bad mood, then it won't taste good. But not physicists. They say if you cook the dinner the same way you did in a bad mood or the good mood, the dinner tastes the same. And physicists in the days of Galileo felt a little bit about time the same way that it was a psychological thing and not a physical thing, and they didn't want to bring time into physics. Also, there was no real measure of time. Nowadays you say, what is time? Well, time is what a clock measures, a good clock. Of course, not any clock. Time is what a good clock measures. But since in the days of Galileo there were no good clocks, the idea that there was good time was a little bit strange. Now you say, well, from the motion of the heavens, the sun goes around, the earth goes around. It turns out, if you look at the motion, say a day is how long it takes the sun to come around again, it turns out that the length of the day is not the same all the time. Some days are longer, some days are shorter. In fact, the Romans defined a day, an hour. The Romans defined an hour as 1/12 of a day. So of course an hour in the summer, where the days are longer, is going to be longer than an hour in the winter when the days are shorter. And I say this to just show you what people's idea of time was. See, if you use the sun, moon, and stars to measure time, sometimes they run fast, sometimes they run slow, and you don't have that idea of some universal, independent variable like time, unaffected by anything. But Galileo nevertheless brought time into physics, and that was the beginning. That was the beginning of physicists using the idea of time. Later on, they decided all kinds of things in physics depended upon time, like the rate at which a body cools depends upon time, or all kinds of, if you have certain radioactive material, how much radiation comes out of it depends on half-life, is based on time and whatnot. But this was the first time that time was brought into physics as an important part of physics, as a main part. And in fact, this even became a definition of time, because the idea in physics of what is time is, well, time is, one interval of time is how long it takes to get a certain speed, and the second interval of time that's equal to the same amount is how long it takes the speed to double. So Galileo's rule eventually became a definition of time as well as a use of time. Now I want to say I wanted to say two things. I have one more important thing to say. Why did Galileo make his mistake and say it gets a certain speed after it falls 1 foot, and then twice the speed after it falls 2 feet? Why did he use distance as the measure? Because it's obvious. Galileo was a professor of what? He was a professor of geometry, not astronomy, not physics, geometry. And so naturally, God too is a geometer. You didn't know that, but God God of course is a mathematician, but what kind of a mathematician does God study? God studies geometry. That's his mathematics. And if you don't believe it, if you ever see these great paintings of God, like in famous chapels, there's God up in heaven, and what does he have in his hand? A pocket calculator? Hell no. Slide rule? No. He has a giant compass in his hand because he's doing geometry. That's the kind of mathematics. And you see that, so God would base it on distance. That's what you would expect. In the olden days, people thought that physics was made of geometry, which is space, and mass, which is the stuff you make things out of. But Galileo had to put time, had brought time into physics because it wouldn't work otherwise. But he was very suspicious. He wondered if he was right. He wasn't quite sure he was right. But then he said, I want to think about something now. And the following question occurred to Galileo. If I'm right and the speed increases in proportion to the time, then let me find the rule for distance. In other words, if I drop an object and it falls for 1 second, it falls a certain distance. Now, if it falls for 2 seconds, how much further is it going to fall? And right away you say, well, if it falls for 2 seconds, it's going to fall twice as far as if it fell for 1 second. But then, because during the second, it's not going at the same speed. Sure, if it was going at the same speed during the second, it would go double the distance, but it's going faster during the second. Therefore, it's going to go further than twice. It's going to go more than twice as far if it falls for 2 seconds. And how much further is it going to go? This is a very important question, because up to this time, in all the things you've been using the rule that you learned in grammar school that distance equals speed times the time. Perfectly good rule as long as the speed stays the same. But if the speed changes, you get into the world that Galileo was entering for the first time. There's 2 ways to get to the answer to this problem. What to do, how to answer the question. And it's such an important thing that we're talking about here that I'm going to answer it in 2 separate ways. First, I'll answer it in the cheap and dirty way. The cheap and dirty way is to take what you learned in high school, and what you learned in high school, or maybe it's grammar school, distance equals speed times the time. And say, well, okay, you have a certain speed and you have a certain time, and that's the distance. Suppose you double the time. You make the thing, and we have a falling body, so it falls twice as far. No, it just falls for twice the time. Now what's the speed going to be? Well, you'd say, well, what should the speed be if the speed is changing? What kind of a speed should we use? Well, maybe we should use the average speed. So we have now speed means average speed. There's a fancy symbol they use for average. To remind you that it's average, I'll draw a line over it. That means it's the average speed. Okay, so it's the average speed times the time. Now what happens if you double the time? Well, the speed starts the same. They start at 0, but it ends up twice as much. Isn't that right? The speed ends up twice as much. So maybe the average value of the speed is twice as much. If the average value of the speed is twice as much and the time is twice as much, you see, and the distance is the speed times the time, you get the idea that if the object fell for twice as much time, it would have twice as much time to fall and twice as much speed, average speed, to do its falling with. 2 times 2 is 4. It should fall 4 times as far. 4 times as far if it just fell for twice as much time. Wow, that's hard to believe, that doubling the time will make the object fall 4 times as far. It's hard to believe. But maybe it's true. Let me look at this thing more carefully. Let me be more careful about this. Let me try to draw a picture. And here's a picture. And I'm going to make a graph. And this graph, this is time. And this is speed. Now let me show you how to use the graph. If something doesn't move at all, its speed is 0. That means its speed is right down here. This is 0 speed. And then it just goes along and its speed stays 0. This is an object that stands still, and maybe it stands still, and you can see, but of course it's going through time, but it's standing still. Now I'd like to show you an object that's going maybe 2 miles an hour. And it's going 2 miles an hour, and it just keeps on going 2 miles an hour, and that's it. Just going 2 miles an hour all the time. And now I'll show you an object that's going 4 miles an hour. It's going here. See, it's going through time, but going 4 miles an hour. Now, I want to show you something else. Let's put some numbers on the time axis too. And let's call this time 0, time 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, rock, 5 o'clock. Now this object starts out at 0 o'clock, otherwise known as noon, and it stays at speed 0. But suddenly at 1 o'clock, it goes up to speed 2, and then it comes along at speed 2 until it's 2 o'clock. Then it puts on its brakes, comes to a sudden stop, and it stays stopped forever. In other words, it's always stopped except between 1 and 2 o'clock, and then it goes for 2 miles an hour for that hour. How far does the object go? Well, you know the answer. Distance equals speed times the time. The speed was 2 miles an hour, and the time was 1 hour. So the distance it went is 2 times 1 equals, it went 2 miles. Okay, now look at this rectangle here. What's the area of this square rectangle? Actually, rectangle's the right word. Well, how do you find the area of a rectangle? Well, you multiply the altitude times the base. Okay, what's the base? Usually the base is measured in inches, isn't it, or feet? But this base is actually not measured in feet or inches. This base is what? It has a certain length from 1 o'clock to 2 o'clock. It's measured in time. The base is 1 hour long. That's the base. Now, what's the altitude of this rectangle? Well, altitude's usually in feet or inches too, but not in this case. In this case, the altitude is a speed. What's the speed? From 0 up to 2 miles an hour. It's 2 miles an hour. Now, if you want to find the area of this thing, of course, you multiply the altitude times the base, and lo and behold, you find that the answer is 2. The area of the rectangle corresponds to the distance that you went. And you shouldn't be too surprised about that, because what is the formula for distance? Distance equals speed times the time. But if the speed is the height of the rectangle and the time is the base of the rectangle, you shouldn't be too surprised that the distance comes out to be the distance that the thing actually traveled down the highway, should you? You shouldn't be too surprised, because it looks just like the formula for the area. The area turns out to be the distance that the thing travels. Let's try it again. Let's change a few things. I want to show you that this really works. Suppose between 1 and 2 o'clock, instead of going 1 mile an hour, the guy had stepped on the gas a little more, gotten up to 4 miles an hour, then hit the brakes at 2 o'clock, come to a dead stop. How much further would he have gone? Well, then the speed would have been 4 miles an hour. The time would still have been 1 hour. And so now the answer would come out, the distance would be 4 miles. And what is the area of this rectangle here? Well, what's its height? Well, its height is, look what its height is. Its height is 4 miles per hour, and the base is 1 hour, so 4 times 1, the area does come out to be 4, just what we want. Now, this idea is more important than that. I want to show you one more thing that it will work. Let's pretend we let the thing go from not from 1 to 2 o'clock, but from 1 to 3 o'clock. Now, how far has he driven? Now let's sum things up. Well, let's understand what's happened here. Cars doesn't move from noon to 1. At 1, suddenly he jumps up at 4 miles an hour, drives along 4 miles an hour until 3 o'clock in the afternoon, hits the brakes, kaboom, the car comes to a stop. How far has it gone? Well, we use the old formula. Here's the old formula. Speed times the time is distance. Speed is 4 miles per hour. Time is 2 hours. 4 times 2 is 8 miles. Has he gone 8 miles? Let's see. Let's look at the altitude of this is, what is it? 4. And what's the base of this darn thing? The base is 2. 4 times 2 is 8. So it works, and it's not surprising that it works. Now, I want to show you something much more powerful than this. We've just been monkeying around with arithmetic. I want to show you something else. Here we are again on the speed and time graph. And suppose the thing comes along like this and goes a little distance, like that. Finally comes to a stop. We want to know how far it goes. So you increase the speed gradually, then you hit a rock and came to a dead stop. Well, again, if you ever had a way of finding this area, you could think it went at a certain speed up to here, so you'd find that area. It went a certain speed up to here, find that area. It went a certain speed here. So that the cumulative area under the whole damn thing, whatever that is, that's how far he went. Of course, I had him going along at constant speeds, but you can think of this as, suppose he went along like this. If you look very closely, you'll see he went at constant speeds there for little tiny bits, isn't that right? But as far as you know, it looks like if you could find the area underneath that thing, you'd still know. Now let me play a game on you. Suppose here, what does this mean? Suppose he came down like that, went down like that, and then came to a stop over here. What does this mean? What's this? This means that he has a speed less than 0. How can you have a speed less than 0? How can you be standing more still than not moving at all? You can have a speed less than 0, if you're going backwards. So this means like minus 2 miles an hour, going backwards. So what you should do, since this is going backwards, you know exactly what to do. This is the forward moving area over here, and this is the backwards moving area over here. You figure this area, and then you figure this area, But to figure his total travel, you got to subtract that from that because that's the backup distance. Yeah. Galileo realized two things that were coming back to the problem of Galileo. Remember, that's how we got into this in the first place. Galileo realized two things. He said, now, supposing an object is steadily increasing its speed. So it starts here, the speed steadily increases until it hits the ground, and then the speed suddenly falls to zero. He said, how far does it go? Well, of course, Galileo said, I don't know, but you could think of it this way. You could imagine that it starts with speed zero, and you could imagine that, it had all these little constant speeds. But still, the problem is, what is the area of this thing? How do you find out? If you could find the area of this thing, you could find out how far it fell. This thing is what? It's approximately a triangle. And you know the rule for the area of a triangle. See, we want the area because that's going to be the distance, and you know the rule for the area. What's the rule for the area of a triangle? It's 1/2 the altitude times the base. Why 1/2 the altitude times the base? Why not the altitude times the base? Because if it was the altitude times the base, then you'd get the area of this rectangle. Altitude times the base will give the area of that rectangle. But you don't want the area of the rectangle. You want the area of the triangle. But the triangle is exactly half the rectangle. So that's the reason the half is there. What is the altitude? The altitude is the final speed. That's what the altitude is. And what is the base? The base is the time the thing has been falling. Okay, so that's it. Good enough. It's a triangle. The speed, of course, the final speed, and you actually multiply the final speed with the fraction 1/2 in front. That's the thing that cuts it down to not the final speed, but effectively the average. See, half of the final speed is going to be the average speed. But now we don't need to do any more mathematics because we've done a wonderful thing. We've done magic. We've shifted from speed times distance to a geometrical picture that the distance must be the area of this triangle. And now forevermore, we can think of it that way, and we can just always picture the area in our mind, and then we don't have to go back to the equation. And let me show you a wonderful thing that you can do with that. We can now answer the question right away. How much further does it fall if it falls for twice as much time? You just make a time and speed picture, and you say, well, suppose it falls for a certain amount of time. It starts with speed 0, and it gets up to a certain speed in a certain amount of time. And how far does it fall? The area of that triangle. It hits the floor and comes to a sudden stop. Now suppose it falls for twice as much time before it hits the floor and comes to a sudden stop. Now it goes along here, twice as much time. See? And now how much distance has it fallen? The area of this bigger triangle is how much distance has fallen now. Well, how much bigger is the big triangle than the little triangle? Well, I'll show you. There's a neat way to see it. Right away you can draw a thing like this and a thing like this, and you can see how many of the little triangles fit into the big triangle. 1, where it fits into itself. 2, 3, 4. Right away you can see if it falls for twice as much time, the distance under the triangle is 4 times as much. It falls 4 times the distance. Probably that's right, but it's amazing. Suppose it falls for 3 times as much time. How far will it fall then? Well, it has 3 times as much time to fall. Yes, not only does it have 3 times as much time to fall, but its average speed is 3 times as great. So its speed is increased 3 times, and its falling time is increased 3 times, and 3 times 3 is 9. So if it falls for 3 times as much time, it falls 9 times as far. 9 times as far as what? 9 times as far as it falls during the first second. And I can draw a picture of that, and I will show you that too. Let it fall for 1 more second. So I will just continue this picture out like this. 1 more second, and of course the speed will continue to grow during that second. And now I will draw in the triangles, and behold, how many triangles are there here now? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times the distance, 9 times the area under the triangle. So that was the rule. This is amazing to me. Every time I tell this story, it always interests me because it amazes me. It reminds me of the first time I heard this story, and it just amazes me. And it must have amazed Galileo. And since Galileo had been wrong on this, how many times had he taken this course on gravity? Had he flunked the course in gravity? He took it once and flunked it with the wind theory, twice and flunked it with the distance theory. This was his third time trying to pass the course. Of course, he was a teacher as well as a student, but he was still trying to pass the course. And even though he had this idea, he wasn't sure it was right because, he couldn't look it up in the book. They hadn't written the book yet. He was the guy that wrote the book, and he hadn't done it yet. So he didn't know if he was right, and it bothered him. And he wondered, and he said, Jesus, maybe I got to do an experiment. You only do an experiment as the last resort. And now he felt so unsure that he felt he had to do an experiment. But how could he time it? He didn't have anything that he could use to do an experiment with. Nobody had still made stopwatches or these electronic watches. Time hadn't moved that far. He had to do an experiment without a clock for a falling body. How can you do that? Galileo realized something. If you hang a picture, and the picture's the least little bit crooked, you can tell. Now, how can you tell? Because you can tell that this distance is bigger than this distance. Now, if I ask you, well, how big is this? Is this an inch, or is it 2 inches, or is that half an inch? You have a very hard time actually telling the distance with your eye. Some people have a particularly hard time. But the eye is very good, not at telling distances, but comparing distances. Comparing this distance with this distance, the eye has no trouble at all, and you can tell that one is bigger and one is smaller, and the thing is not level. Galileo worked with his father to do experiments when he was a kid, and remember, his father was a music theoretician. And Galileo knew one more thing from that experience, that as the eye is good in comparing intervals of space, the ear is good in comparing intervals of time. You have no effort at all in telling which of those claps came at an interval where it shouldn't have, do you? You say, gee, any kid could do that. It doesn't take any great wisdom. And why is that? You could perhaps not really tell the interval of time between the claps, but when one clap came a little bit too soon, you could tell that without any trouble at all. The ear is good at comparing intervals of time. And that's what Galileo took advantage of in an experiment, the most ingenious experiment in the world that he did. And I want to show you what he did. Here's Galileo's experiment. What he did is this. He took a board like this, and he put it on an incline to make it so the bowling would come down a little bit more slowly. That would be nice. You could do, I guess Galileo used to talk to God. He'd ask God if he'd give him a bigger eye, like a cow, and God wouldn't, so he figured out how to do it artificially. And Galileo must have figured out that if God would make objects fall slowly, then he could time them, even with his crude clocks. But of course, God wouldn't, then Galileo figured out how to make things fall slowly by rolling them down. And of course, to make sure that they didn't get lost on the way down, he cut a groove, and here's a groove, and a groove in here. And there's the groove in a board. See, you could, and then Galileo put a cannonball up here at the very top and let it roll down. A big old heavy ball, big heavy thing up there. And he let it roll down. And then Galileo took a knife out and put knife marks at equal intervals along the edge here, like this. Now, if you cut knife marks at equal intervals along the edge, and you roll the ball down as it hit each one, go click, click, isn't that right, as it went over those little irregularities? And let's pretend you actually let it roll down. I want you to tell me what it would sound like. Would it sound like click, 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 click? See, they're evenly spaced, so you might expect that the sound would be evenly spaced in time. Is that what you'd get? Maybe you disagree. Well, would it go like this? Click, 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 click? Hell no, that's exactly wrong. It's going slower. This is what it would sound like. If you rolled it down, it would sound like this. Go click, 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 as it goes faster and faster. That's what it would sound like. Galileo didn't want that. Now I'll show you what Galileo did. Galileo did this. He didn't cut the board like that. This is how he cut the board. Galileo went a certain distance down from the very top, tiny distance, and he cut one with his knife. And then he came down from the top, not twice as far, but how much further? He came down 4 times as far. From the top, 4, 1, 2, 3, 4. And he put a second click, and he cut it there. And then he did it again. He came down from the top this time. How many times from the top? 9 times. He came down 9 times. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right there, he put another mark. And how far would the next mark be? If there was room and you put it on there, how far would it be down? Well, you know, first one was 1, then 4, 9. That was the third one. The fourth one, it would have 4 times the speed, and 4 times the times would be 4 times 4 would be 16 times. 4 times 4 is 16 times as far down. And then Galileo went and he took this apparatus and he went into a room and he closed the door so he wouldn't hear any sounds. And then he turned off the light so he wouldn't have any distractions. And then he closed his eyes so he would be at peace with himself. And in the dark, he stood there in that room, and he put that ball up there, and then he let it go. And he just listened with his ears alone. And what did he hear? Click, 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 click. Evenly spaced clicks. And he knew he could accurately tell with his ear alone if the spaces were evenly spaced. The clicks were evenly spaced. All it took was an ear to tell that. And there, standing in the dark, in a dark room with his eyes closed, he knew that he was right. He had done the critical experiment. It is true. The speed does increase in proportion, not to the space, but in proportion to the time. And that was it. Often you hear people saying that schools don't have adequate equipment and they should spend a couple thousand more for some fancy piece of junk that won't work very long anyway, like a Christmas toy for a kid. Here's something that one of the greatest experiments in the world was done. Any poor California school district ought to be able to afford to do that experiment. Doesn't take a lot of money. Doesn't even take a clock. I want to ask you an experiment, a question. Suppose Galileo had done this experiment on the moon. Would it have been different? Yes, the clicks would have been further apart. They would have been further apart. Would they have been even spaced? Yes, the timing would have been, the time intervals would have been the same. Suppose the board was steeper. Then the clicks would be closer together, but the clicks would be evenly spaced. The essential thing is that the clicks are evenly spaced in time, and it doesn't matter if you do this experiment on the moon or where you do it. In fact, just for the heck of it, I'd like to tell you how Galileo expressed the law of gravity. He expressed it in the following way, and I just am telling you this sort of for the heck of it. It doesn't have any scientific value, but an object falls let's say it starts out at distance 0, it falls to distance 1, then the next time interval it falls to distance 4, then to distance 9, then 16, and that next would be, 5 times 5 is 25. I want to show you something. If you look at how far it falls in the first interval, from 0 to 1 foot, that's a 1 foot fall. From 1 foot to 4 feet, that's a 3 foot fall. From 4 feet to 9 feet, that's a 5 foot fall. From 9 to 16, that's a 7 foot fall. And from 16 to 25, that's a 9 foot fall. And this is how, see, what have you got here? 1, 3, 5, 7, 9. Those are the odd numbers, aren't they? The first odd number, the second, third. Those are all the odd numbers in sequence. And this is what Galileo wrote down. He said, the intervals through which an object falls in successive equal intervals of time are to each other as the odd numbers. That's what he said. Isn't that a neat way to say it? He didn't say anything about feet per second or meters per second, because he knew if he said it in feet, somebody would change it to meters someday and then change the meters to something else. He didn't even say on Earth. Wouldn't the same rule hold true on the moon? The way he said the law of gravity was he said it for all time. The way he said it, you don't have to worry about the units. You don't have to worry about the planets you're on. The intervals of space through which an object falls in successive equal intervals of time, whatever those intervals are, hours or seconds or microseconds, are to each other as the odd numbers, regardless of what units you're using or where you are. Well, anyway, all this rolls out very easily because I've been through it before and because I'm following in the footsteps of Galileo. But when Galileo thought it through for the first time, he had to do a lot of hard thinking. Well, now that I've told you about this, I have something else, some closely related things I want to tell you about. And here's the question I want to ask you. If I have a rock and I throw it up in the air at a certain speed, it'll go up, come to a stop, and then it'll fall back down again. Now, if I throw it up twice as fast, same rock, twice as fast, it'll go up higher, and it'll take longer to get up there, and it'll take longer to come back to the ground, but it'll come back to the ground too. And now I want to ask you a question. Never mind about the down trip. I'm just talking about the up trip, when it goes up and comes to a stop. It comes to a stop just for a moment up there, just for a moment. And I want to ask you, if I throw it up twice as fast, it goes higher before it comes to a stop, doesn't it? How much higher does it go if I throw it up twice as fast? How much higher? And it also takes longer to get there, isn't it? If I throw it up twice as fast, it takes longer before it gets to its peak, doesn't it? How much longer does it take? Now, I know you say, hey, Epstein, don't ask us that. You know, you gave a lecture on falling bodies, finished your talk. It was a nice talk. No sooner do you finish the talk than you give a little examination. And you ask about, not about falling bodies, but about bodies going up, which you didn't talk about. So what the heck's going on here? But it turned out you know the answer. You know the answer to this question. And I'm going to show you how you know the answer. You know the answer by a most powerful method that's used over and over and over again in physics. And let me show you what it is. Supposing that I have a ball here, and let's suppose that this ball is a perfect rubber ball, or maybe it's a steel ball bearing, and it bounces, boom. And you make a movie of it as it bounces. And maybe it bounces again, boom. It's a perfect, each time it's just perfectly elastic, comes right up to where it was. And then after you make this film, you come in, and somebody's going to show it for you. They're going to project it on a screen. But they're going to ask you a question. They're going to ask you if you can tell if the movie that they're projecting is running forwards or backwards. Maybe they'll pull it. You don't know. There's a 50% chance they might run the film backwards, and you have to sit there and look at it and tell. Could you tell? And the answer is no. If that ball bounced exactly up, and you can see it in your mind, and you made a film of it going up and down, each time it bounced back just as high, and you made a film of it and ran it backwards, it was just as if the film were running forward. And that tells you something. There's an important lesson in that. It means that the backwards motion, the motion of the ball as it comes up, is exactly the time reverse of the motion as it falls down. So if you make a motion of a ball falling down and run it backwards, it will look exactly like what a ball does when it goes up. So you've learned a double lesson. To make this idea in physics of running time backwards work, there's one extra condition you have to have. The bounces have to be perfectly elastic. If you had a ball that was imperfectly elastic, and it went bounce, boom, 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 boom. Then if you made a film of that and ran that backwards, you'd see the ball would begin bouncing like this, and it would get higher, and you could tell that real balls don't do that. You'd tell that that's obviously the film running backwards. So in the case that there's friction, you can tell if the film is running forwards or backwards. But if there's no friction, then you can run the film backwards, and it will give you perfectly good physics. Well, and this applies not only to simple things like dropping rocks and balls, it applies even to complicated nuclear processes. And it's really a powerful way to think about things, to solve problems that you wouldn't think you could solve otherwise. And you can also get in trouble with it because sometimes there is friction where you don't think there is. But anyway, so the problem of throwing the rock up is exactly the same as dropping the rock down. Well, first of all, let us throw it up with twice as much speed. If you throw it up with twice as much speed, how much more time will it take to get up to where it's coming from? Well, let's reverse the question. If it's thrown up with twice as much speed, then if it fell down, it would be falling down with twice as much speed. How much more time must an object fall in order to get twice as much speed? To get twice as much speed, it must take twice as much time. So it means that if an object is thrown up with twice as much speed, it will take twice as much time to what? Twice as much time to get up to the place where it's going to come to a stop. So if you throw it up twice as fast, it takes twice as much time to get up. It also takes twice as much time to fall back down again, too. So it's twice as much either way. Now let's suppose you throw it up with twice as much speed. Not how much more time does it take, but how much higher does it go? How do you answer that? We say, well, it falls for twice as much time on the way down. If it falls for twice as much time, we know it falls 4 times as far. So it must go up 4 times as far too, just the reverse of that. And it's true, if you throw an object up in the air with twice as much speed, it won't go twice as high. It will go 4 times as high. And that's also an amazing thing. The more, you think about that at first, that's an interesting toy to play with in your head. And if you throw it up 3 times as fast, how far up will it go? It will go up 9 times as far. It'll go up 9 times as far. Yes, indeed. I'm going to tell you the most important thing in the whole lesson in physics that I've taught so far. This is the most important thing that I have to tell you. Because so far all these things are sort of academic interest. They're very interesting, but they have to do with space and rocks and thoughts that people thought many hundred years ago. But what does it have to do with making a dollar? Not much. But now I'm going to talk about something that relates to the world that you live in. And this is the question I'm going to ask. Suppose you're driving along in a car and you have a certain speed of the car, say 20 miles an hour, and you hit the brakes. It takes a certain amount of time to stop the car. It also takes a certain amount of distance to stop the car. And now, suppose that the car is coming along not at, 20 miles an hour, but suppose it's going twice as fast, 40 miles an hour. And suppose your reflexes in both cases were instantaneous. You were Superman, so you hit the brakes just perfect right away. But now the car is going twice as fast. So it's going to take more time and more distance to stop the car. And I'm going to want you to tell me how much more time it takes to stop the car when it's going twice as fast. And even more important than how much more time, I want you to tell me how much more distance it takes to stop the car when it's going twice as fast. How can we reason out what the answer is? Well, we already have the answer. You see, when you throw a rock up in the air, what stops it when you throw a rock up in the air? Well, there's a certain constant force pulling on it. In fact, if it's a 3-pound rock, what's the force that's pulling on it? 3 pounds, continuously, smoothly pulling on it, making it go slower and slower and slower until finally the rock stops. The same thing's true with a car. When you hit the brakes, what's making it stop? Somehow, due to the friction and the drag and the brake drums, there's a constant force pulling backwards on the car. And it makes it go slower and slower and slower until gradually it drops from 20 miles an hour to 0, or 40, it finally drops to 0. It's exactly the same as stopping the rock. The only difference is that the car is moving sideways instead of the rock moving up and down. There's a difference in direction. And in one case, it's the force of gravity that's bringing it to a stop. In the case of the car, it's the force of friction. But other than that, it's the same mathematically. Mathematically, the problems are the same. And so knowing the answer to the rock question, we automatically know the answer to the car question. If you throw the rock up with twice as much speed, how much more time does it take to stop? Answer with the rock is twice as much time. And the same with the car. If the car doubles the speed and you hit the brakes, same car, same road, same reflexes, same everything, but it's twice as much speed, it takes the car twice as much time to stop. But how much higher does the rock go? How much higher does the rock go? That we know. It's not twice as high, it's 4 times as high. And that's the important thing with the car. When you stop a car, it doesn't matter how much time it takes to stop. What matters is how much distance you go down the road. And if the car is going twice as fast, it doesn't take twice as much distance to stop the car. It takes 4 times as much distance. And if you go 3 times as fast, if you got the car from 20 up to 3 times 20, which is 60, then it doesn't take 3 times as much distance to stop the car. It takes 9 times as much distance. And that's such an important idea because your life depends on it, as well as your dented fender and bumpers. I want to draw a picture of it. mathematical picture of it. Here is the old speed and time graph that we talked about. And you start with a certain speed, say 20 miles an hour, and you bring the car to a stop. See, the speed of the car goes down and boom, it stops after a certain amount of time. And the speed is then down to 0, down at the bottom. And the distance that it went is the area of this triangle, just like before. Only the speed is getting less as you go down. Let's take this case. Suppose you start out with the same car, but it's going twice as fast. The brakes are going to work the same, so they're going to eat the speed at the same rate. You're going to descend at the same rate and strike 0 over here. How much more time did it take to stop the car? Twice as much time. But how much more distance did the car go? It's the area now of the big triangle. The area of the big triangle. How many little triangles make the big triangle? 1 into itself, 2, 3, 4. Double the speed and 4 times the distance to stop the car. That's something to take home and to think about. It's interesting. All this straight from Galileo. Automobile braking from Galileo. No more physics than Galileo. Even if Newton had never lived, that problem could be solved just using Galileo's view of the world. But it's even more powerful than that. I want to tell you something else. Suppose that I have a gun and I fire into the wall. Wham! It's going to make a hole in the wall. Bullet's going to go in a certain distance, chewing out wood or chewing out brick, and the bullet's going to stop. And then I could measure the hole, be a forensic scientist, and you measure the hole and see how far the bullet goes into the wall. Now I want to ask you something. Suppose you took a gun, and this gun could shoot a bullet twice as fast, just twice as fast. And again, you go up to the same wall, different place, wham! And you make a second hole. This bullet's going twice as fast when it hits the wall, though. Make a deeper hole? Of course, deeper. How much deeper? Well, now you got to be careful. You got to think. You don't want to jump to anything. There's a certain force that brings that bullet to a stop as it goes through the wall. Isn't that right? It's pulling the wood apart, and there's a certain force on it. And if it goes in there twice as fast, the force is the same. But so it's going to go further. How much further? It has to be brought to a stop. It'll be 4 times as far. It'll make a hole 4 times as deep. 4 times as deep. I think, gee, that's amazing. All you have to do is make a bullet go twice as fast. It'll be able to penetrate armor 4 times as deep. Wow, that's an amazing thing. I want to show you something. In order to make it go 4 times as fast, of course, it would take a different bullet, wouldn't it? Because a certain bullet has a certain speed. Only way you could make it go 4 times as fast was by putting more gunpowder behind the bullet. Let's draw a picture. Let's draw a picture of what a bullet looks like. The bullet has a lead part, and then there's some powder behind it. And there's a picture of a bullet. It has a certain speed when it's fired through a gun. Now, suppose you wanted to make that bullet go twice as fast. Of course, it'd take more powder. You'd say, well, how much more powder? Well, you'd be tempted to say right away, wouldn't you? Tempted to say, well, what we'll do is just twice as much powder. That'll make it go twice as fast. But remember, to make it go twice as fast, you have to how could you make an object go twice as fast? Well, one way to make an object go at all, in fact, the only way we really know, mathematically understand how to make objects go is to drop them. Isn't that right? That would be another way to make an object go. You have to lift them up to drop them. And if you want to go 4 times as fast, if you want to go twice as fast, not 4 times as fast, if you want to go twice as fast, how much further do you have to lift it? Well, if you want it to go twice as fast, you have to lift it 4 times as far. Isn't that right? 4 times as far. And if you're going to lift it 4 times as far, the same object, you're going to have to do 4 times as much work. How do you know? Because we already know what work is. Work is foot-pounds. Isn't that right? So much weight lifted so much distance. And if you make the number of foots 4 times as great, you're going to make the amount of work 4 times as great. So it's going to take 4 times as much work to make the bullet go twice as fast, if it gets its speed just by being lifted up and dropped. And it turns out that one way of getting speed is more or less the same as another. And so it does take 4 times the energy to make the thing go twice as fast. So that means that you can think of each unit of powder as being able to do a certain amount of work, like a certain amount of gasoline. And if it's going to have to go 4 times as high or twice as fast, it's going to take not twice as much powder to get it up there, but it's going to take 4 times as much. So when you see the bullet, you say, well, after all, that's the bullet that makes it go twice as fast. So, gee, since the bullet's 4 times as long, maybe it's not all that surprising that it makes a hole in the wall 4 times as deep. In fact, there would be another way to make a hole in the wall. If you think about it, after all, the bullet is really nothing but a messenger. What do I mean by it's nothing but a messenger? Well, the energy comes from here. The energy is put into here. This thing carries it and delivers it to the wall. Maybe you could dispense with the messenger. What do you mean, dispense with the messenger? Well, take the bullet out and throw it away. Take this powder here and use it to melt the wall or burn the wall. You can actually, sometimes that's done in welding or cutting. They have a torch and they just take a certain amount of dry powder and they use it for burning a hole. So you can actually use that powder for melting or burning the hole into the thing. And we know that if it goes twice as fast, it's supposed to make a hole 4 times as deep, which isn't surprising because if we dispensed with the messenger and just used the energy straight to burn or melt its way through the wall, it's not surprising. There's 4 times as much. So it's not surprising that the hole is 4 times as deep. It's amazing that Galileo's idea will extend so far to explain such things that you would think are more complicated physics. I'm now going to show you one final thing that Galileo was able to do with his understanding of falling bodies. Because remember, this whole talk is just based on Galileo's understanding of not the why, but just the rule for falling bodies. Just the rule that if you double the falling time, you get 4 times the distance. And by using that rule, Galileo was able to solve one of the problems that had baffled people up to that time. In fact, it's a problem that Leonardo da Vinci worked on. And it's the problem of finding the path of a cannonball. Leonardo spent one heck of a lot of energy on this, and he had several different ways of doing it. In fact, he had so many different ways of figuring this out that led to different answers that I dare say maybe among all the ways, one of the ways was the right way. And the problem was a very important problem in the days of Galileo because they'd had cannons for quite a while by then, and by then they probably had pretty good cannons. If you fire a cannon, one of the things you wonder is a mathematical way to find what the path of the ball will be. Of course, from the point of view of the mathematician, you're very interested in the path. But of course, from the practical point of view, what you're interested in is the range of the cannon. Given this angle and given some speed, what you wonder about is to find out the path of how far it will go. Maybe you can think about that. If you all Galileo knew up to then was the rule of the falling body, just what I've told you. And of course, the cannonball is a falling body, but it's also a going up body, and that's all he knew. And he was able to solve that problem that everyone, including Leonardo da Vinci, could not solve up until then. And I'll show you how he was able to do it. And maybe you can figure it out for yourself, and that's what we'll talk about next time.